So, do you want to jot these down for me? Cool. All right, so now that you've got that down, like this initial part over here, that was just looking at, like that's actually what we did over here, right? This is just like a formalized way of doing it, would you agree? Right? It's just saying, hey, okay, if I want to find one of the solutions, what I need to do is I take the argument of my original complex number, I divide it by n, okay? And the same thing with the modulus here. I take the nth root of that original modulus, and that will give me one of the solutions, right? But what's the problem with that? The problem with that is that it's only finding one of them. How can we find the others? How do we find the other possible values of z? Well, what we can do is, and this is where you might want to take the cos or I sine theta approach, or you might want to write this in the Euler form. Both are fine. Cambridge typically writes them in the cis form. But how we can approach this is, let's take this idea, this initial value here. Let's say that, okay, well, if we have z cubed is equal to 8i, right? Then to find all of the other solutions, what I want to do is I want to think about how can I suppose, rewrite 8i in my exponential or cis form, right? So that's what I want to be thinking about. How can you write 8i in your cis form or exponential form? Well, we can say that z cubed would be equal to, now we actually already know all that information, the argument and the modulus, right? We can say it's equal to 8 e to the pi on 2 I, right? So that's what we can do here, okay? But remember, this is the thing that we introduced with the roots of unity and how we can find the multiple solutions. Is there another way we can write this? In the sense of, particularly like its argument over here, right? Is there other forms that we can write this in, which is still equivalent? Polar form? Yeah. Well, this is kind of like the polar form, right? Because you've got the modulus and the argument. But remember, thinking about like our rotations, how they're equivalent. Do you remember we had to do something to consider the other solutions as well? If you think about, if you take a full rotation, it's still the same complex number, right? But the argument would technically be different. How do you get that full rotation again? 2 pi, yeah, exactly right. And this is how we're going to find the other solutions. Here, what I'm going to do is I can also write this as pi on 2 plus 2 pi, but not just one revolution. You can take any values of 2, any kind of multiple of 2 pi, and you would still get the same solutions. That's kind of how I'm going to approach this here, right? And so now at this point, you can start to see where these steps come in, right? What we can do is we can, if I'm taking this all to the power of 1/3 now, no, that shouldn't be an e there, it should just be I. If I take this all to the power 1/3, right, what happens is, well, I get the cube root of this, which is 2, and then I'm dividing this whole expression here by 3, which gives me pi on 6 plus, what's that, 2 pi k on 3, right? And so hopefully you can see now where this first solution comes from through this algebraic approach. If we just let k is equal to 0, well, this whole thing goes away, and we just get left with that first solution at z1, right? So let's go ahead and find all the solutions. And remember how I said that there is a formal way to try and find what this is going to equal to. I typically just substitute in values around 0, or you'll find that if you just substitute any 3 values, really, you just have to do a bit more algebraic work to find the principal argument solutions. So whichever way you prefer. But I'll just do when k, because I'll use the k method, right? So k equals to 0, let's try. So we'll get z is equal to 2ei to the power 6, we already found that one. Do you want to give me another value, Cameron? K is 1, so we're going to get z is equal to 2ei. Can I do that in my head? 4 pi on 6. 5 pi on 6? Is that looking right? That's what I'm getting. You let me know if you get something different. You got it? And do you want to try k equals to -1? What's that going to give me, Alyssa? Negative 5 pi on 6. Yeah, that's probably right. That would make sense as well. Okay, so at this point, right, 3 solutions. So maybe you want to call them Z1, Z2, Z3, right? And let's just think about this, right? So what we found is we found one solution that we already knew that we had, but then these two over here, where are these going to live? Well, 5 pi and 6 around here. That looks pretty good. So what's that? 2ei to 2ei, 5 pi on 6. And then how did we get this solution? This one here was when it was -1. So pi on 6 minus 4 pi on 6. Wait, -1, sorry. So minus 2 pi on 3. What are we getting for that one? -3 pi on 6? Then we're getting pi on 2? No. What did you get for the last solution when k is -1?
Should be pi on 6 minus 2 pi on 3.
Yep. And then what does that give us? Minus pi on 2. Is that what you guys got? Sorry. Wait, did I write something wrong?
No, I kind of quickly jumped to this.
Okay.
This is probably
Okay, yeah. I was just a bit confused there because I was thinking whether, and this is a good thing, right? Like just with equations as well, you should be able to have a check as well. Because one thing that I was a bit confused about was, well, where's negative pi on 6? Well, that would be like kind of here roughly, right? And we already know that our solutions, they should be equally spaced apart. So, I mean, there are checks you can do. That's why the visual thing is kind of good, actually. It's pretty hard to check the solution to this algebraically, for me personally. So that's why I like the visual way of saying, oh, okay, do these actually match all the things that I'm supposed to do? So, did you get that one, Cameron? Was that pi on 2? Yeah, okay, cool. Yeah, sweet. So, probably around here now, roughly, okay? So, boom. And so that's going to be 2e negative pi, I pi on 2. All right, cool. These are our sort of 3 solutions around there. And hopefully now you can start to get an intuitive sense of what's going on. We've got these 3 solutions all spread apart. And we can see that if we cubed any of these individual ones, then that's how we would get 8i over there, right? So you could like cube all these moduli, you'd get 8. If you added these arguments by themselves 3 times, you multiply them by 3, you would get to pi on 2 as well, okay? Any questions about that one? That's A and B there. Part C is interesting. I want you to try that one. Part C, we want to find the sum of the roots. And the reason why I want you to do that, there's an interesting relationship between these that we're going to have a little look at. But I want you to have a go at that yourself first, and then we'll come back in a second.